In this class, we study the first law of thermodynamics. The first law of thermodynamics is nothing but conservation of energy. And even before we reach the point we studied the first law of thermodynamics is equivalent to the input energy subtracted by the output energy is the remnant of the energy. That's it. And another important point in the first law of thermodynamics is the equivalence between the heat energy and normal energy. And when we study the energy concept for the dynamics of a point particle, we consider the kinetic energy that is the explicit form of energy that is revealed by the motion of a particle. And according to work kinetic energy theorem, we have found that the work done on a system is can be converted to the kinetic energy if there is no other external force contribute to the particles. And because of this, the work kinetic energy theorem, the work is equivalent to the energy. We have another aspect of energy that is called the potential energy. That is not explicit, but is implicit. It is hidden in somewhere, and it produces its energy as an explicit form that is kinetic energy. When a particle's orbit returns to the same point, the hidden energy is returned. So that is related to the fact that conservative force, a particle under conservative force making an orbital motion, the potential energy, because the potential energy is the function of position only, that there is no change in the potential energy when it returns to the same point. And during the time, the variation of potential energy is cancelled when it returns to the same point. So if we look at only a partial aspect, that is the explicit form that is called the kinetic energy, it looks energy is not conserved. However, as soon as we introduce the concept of the potential energy, as far as the conservative force is concerned, we can say the total mechanical energy is conserved as long as the force is a conserved force. The conserved force, we can determine whether a force is conservative or not by considering the fact that curl F equals 0, that is irrotational. When we learn thermal physics, we have one more additional implicit energy that is called internal kinetic energy. A system of particle has energy. It just for simplicity, we forget about the potential energy. In that case, the system of particles has a total kinetic energy. And the total kinetic energies can be expressed in terms of the sum of the kinetic energy that reflects the total mass concentrated at the center of mass There's 1/2 mv squared, where v is the center of mass of velocity. And that center of mass, that kinetic energy, disappears when we make a Galilean transformation to from an arbitrary system to the center of momentum frame. Even in the center of momentum frame, a system of particle, a system of particles may still have a kind of kinetic energy that is due to the relative motion with respect to the center of mass. That is the internal kinetic energy. Internal kinetic energy. If a system is simple enough, such as a rigid body, the internal kinetic energy is simply calculable. However, if the relative motion of every particle with respect to the center of mass is rather complicated, such as the gas, we know the motion of molecules inside the gas is randomly distributed. It is impossible to track every particle's form, the three momenta. So it is rather complicated. However, we can say something. Internal kinetic energy has absolute minimum. Why? The kinetic energy is the sum of the positive values. At most, at least it is zero. There is, it is impossible to have a kinetic energy to be negative because it is 1/2 mv squared. 1/2 is the positive number. M is the mass, that is positive definite. And velocity squared, that is a v1 squared, v2 squared, v3 squared sum. Velocity squared, the real number squared, is a positive definite. Therefore, if every particle is frozen, relative, it does not make any relative motion with respect to the center of mass, then the internal kinetic energy vanish absolutely. Our idea of statistical view of thermal physics is that the internal kinetic energy, the average value of the internal kinetic energy, can be treated as the temperature. And at the current stage, our physical definition of temperature is just like that. Average kinetic energy of molecules in units of Boltzmann constant Kb. Okay, that is our beginning, starting point to study the first law of thermodynamics. Before we begin, we just refresh our mind with some keywords. We will see cylinder frequently. This is to simplify the analysis of changing volume of a gas. It is contained in a cylinder. In case it is contained in a cylinder and it is variable, only one position of a piston attached to a cylinder. The piston can translate with some distance, and there is a fixed cross-sectional area. Then it is very easy to analyze the volume change. This is the x height of this cylinder. Then this is volume, is a times x. And change in volume due to the displacement of this piston can be described as a dV. There is a cross-sectional area multiplied by the change in the height. In general, it is not required to choose the container of the shape of cylinder. It is just to simplify the analysis. Next, we frequently use insulator. Insulator means it blocks the heat flow between environment and a system. And our system is mostly gas. It has a variable volume rather than the fixed volume for the solid or liquid. So our main interest in main interest in this uh, from now on is concentrated on the gas mechanics. Weight is used to control the pressure pressing down in the lid of the container, mostly made of a cylinder. So weight is used to control the magnitude of the pressure. We also have frequent use of thermal reservoir. Thermal reservoir is anything that contains enormous amount of heat with constant temperature. So temperature is controlled by heat reservoir, and even though it may give away or accept heat, its temperature doesn't change simply because it contains an enormous amount of heat. So when we want to make a thermal equilibrium of our sample that is relatively small, it is usually good to attach that sample in thermal equilibrium with the thermal reservoir, keeping the temperature the same, and let it vary its own volume very, very slowly, in order to keep the equilibrium always, and only if the state is in thermal equilibrium, any kind of thermomechanical variable, such as volume, pressure, temperature, that are well defined. If we shift the piston in a very fast way during the transition between the initial and final stage, the pressure, the volume, and temperature may not be defined. So we are not able to keep track on the change of the kinematic variables for the thermodynamics. So these are basic concepts we have to keep in mind in the rest of the analysis. Next, we would like to separate environment from our main concern, that is a sample of gas. Okay, so when we consider a sample of gas, we need to know the volume, the pressure in it, and then we can the if the gas is contained in a cylindrical container with the cross-sectional area A, and the piston translates by amount of dx, then the change in volume of the gas is the cross-sectional area A multiplied by dx. So therefore, the volume change dV is A times dx. The volume change is simplified in that case. In addition, because the pressure inside a container should be the same everywhere. Sure, if it is a liquid under constant gravitational field, the pressure of liquid changes depending on the depth of the liquid level. But for gas, its density is very low, if you unless you consider amount of gas from the surface of the Earth until a few kilometers, something like that, a very large scale, then we may have to consider the pressure change depending on the height. But for this kind of very tiny relative to the large scale amount of air that varies, whose pressure varies depending on the height, it is almost constant. So the pressure is, we assume the pressure inside this container is fixed to be P. Therefore, the force applied to the work is the area multiplied by the pressure. This is PA. So if I multiply pressure both sides, PA is the force and FDX is the work done by the gas inside the container when it expands by volume dV. So our first identity, the work done by the gas, is the pressure multiplied by the change in volume. If the volume change is positive, then it is expansion. When a gas sample expands, it does work. So it does work. If there is no energy supply, then the gas loses its own energy. And the energy of the gas is the kinetic energy. The sum of the kinetic energy of all molecules contained in the container. Therefore, it is proportional to the temperature. So if there is no energy supply, then when a gas expands, gas works and loses its own energy. Therefore, the temperature will be go down. Will be go down. Okay. This is true for the general shape of gas. That we consider the simple case for a gas contained in a simply shaped container, such as a cylindrical container. But it is also possible to compute the work done by the gas that is contained inside a spherical container or any any shape. So what we want to do is consider the force applied to a small patch. The force is pressure multiplied by area. In case the surface direction of the surface varies, then we have to integrate over the whole surface. So this is a way to compute the work done by gas when the surface is not flat but variable. Free expansion. The work done by gas against a vacuum. You can see this originally gas is contained in the one half of this container, and the other half of the container is empty. That is a vacuum. Vacuum does not produce any pressure. The equilibrium is made by another force, but vacuum is impossible. It is impossible for vacuum to apply pressure against this gas. So I need another external force to hold this gas in it. And why don't we open this partition? So at some time later, it can reach a thermal equilibrium to have every molecule distribute over the whole space that is twice the original volume. How much is the work done by the gas during this expansion? The answer is 0. The reason is that the work done by some force is a positive only if there is another force against it. I mean, the interaction between two objects, it follows the Newton's third law, action and reaction. If there is nothing against to be in equilibrium, then I do not have, I'm not able to apply any force at all. Okay? So, according to action and reaction, the free expansion does not require any work done by a gas. Isobaric process is a constant pressure process. As the word barometer that measures the pressure, BAR means pressure, and ISO means equal. So of equal pressure. During the process, the pressure is controlled to be constant. So although outside empty, somebody is holding the lid to with the force F equals PA from the beginning until the end of expansion. So P is now controlled with as an isobaric process. We are keeping the pressure the same. When the pressure is kept the same for whatever reason, the work done by the gas is the pressure's integral over volume. However, pressure is constant, it factor out of the integral. So this is a simple integral is total differential from the initial to final. So the answer is the finite difference of the volume change. Next, we consider isothermal process. Isothermal means temperature is equal. So constant temperature process. In an isothermal process, temperature doesn't change. Because temperature doesn't change, internal energy of the system doesn't change. Because the gas does expand, it has a positive work. If you spend energy by working against some external force, the gas loses its own energy. However, it is isothermal process that keeps the temperature the same. Its internal energy is the same. Aha, that means the same amount of energy that is equivalent to the work done by the gas must have been supplied from outside. That is in the form of heat. That's the reason why the heat reservoir at temperature T is given in here. It has supplied heat with the same amount as the gas has not with PDV. Okay, the then amount in constant temperature process that is governed by the phenomenological law called the Boyle's law. Boyle's law states that PV is constant when temperature is fixed. It is constant. If it is constant, pressure is constant over V. So the work done by the gas is PDV, and that is log times constant. The later in the next class, we study ideal gas law. We will find that this coefficient is NKBT. So this one is a log. It's a, so we have log, natural log, final volume divided by the initial volume. So this is the isothermal process. In this process, the heat should be transferred to the uh, gas, and gas has done work by this amount, and this exactly the same amount of heat must have been supplied from the heat reservoir. Next, we consider the work done by a gas in a cyclic process. In order to compute the work done by a gas, it is convenient to draw a diagram, a PV diagram. In that case, because the work done by the gas is PDV integral, the area below the curve from A to B, this area is the work done by the gas. If it is this is a cyclic process, so when the path is going from A to B, this is the work done by the gas during the process from A to B. The work done by the gas from A to B under this curve, the curve, a lower curve, this is the area. In the cyclic process, it is from A to B, and then B to a different path. In that case, this integral is a negative. This is negative, right? So this integral is a negative value of this integral. Therefore, this one subtracted by this blue area is the area surrounded by this curve representing the cyclic motion. If it were in opposite direction, in this direction, then the work done by the gas becomes negative. This area is a negative, and this is positive. So this cyclic path will give the work negative, and this is a positive. Okay. So this is the summary. Next, we consider heat capacity and internal energy. The internal energy is total kinetic energy plus a total potential energy. And in here, uh, the total kinetic energy represents the vibration, and the total potential energy represents the latent heat. If it makes a phase transition, it requires to compress some spring that represents the binding energy of system, and this is related to latent heat, the heat heat of transformation, and this is the vibrational kinetic energy in the case of a liquid or a solid. In the gas, there's the kinetic energy is solely for the translational motion, but it is in very high energy. It can rotate and as well as it can vibrate. The molecule itself can vibrate. Anyway, internal energy is the sum of all these kind of things. And in case we have a system that has a invariant volume, such as a solid, in that case, the total kinetic energy, total internal kinetic energy, is change is exactly the same as the input heat because the gas does not work at all. So it accepts the heat from the environment and then it loses energy by working, but it does not work because dV equals 0. So dW is PdV, that is 0 too. Therefore, as soon as it accepts energy as a heat, the system acquires energy, and that is transformed into internal energy. And that internal energy changes its temperature, and overall coefficient is called heat capacity. And the heat capacity can be measured by fixing the volume, the supply energy, and look at the change in temperature. And this will be the way to evaluate the heat capacity of a system. In PV diagram, later we will study, in the next class, we will study the PV equals NKBT, that is the equation for ideal gas. Here, capital N, this uh, P is pressure, V is volume, and capital N is the number of molecules, and Kb is the Boltzmann constant, and T is the temperature. Sure, only if the system, gas system, is in thermal equilibrium, pressure, volume, and temperature are all defined. If we know this ideal gas equation, we can determine the temperature by dividing PV by number of molecules and Boltzmann constant. So this is a repetition. Finally, we study the main theme about this class, that is the first law of thermodynamics. The first law of thermodynamics is nothing but the conservation of energy. Actually, I have repeatedly told you this. This is input, and this is output, and this is remnant. If it accepts the heat from the environment, the red one is a heat reservoir that supplies the energy to a system. If it accepts the energy, it give away. It gives away some energy by work. It does work as a PDV. So if the volume of the gas increases, the gas does work. If volume decreases, the gas does the work in negative sense. Anyway, it accepts and it gives away, and remnant is for the change in the internal energy, internal kinetic energy of the gas. So that results in the temperature change. If we keep the volume dV equals to 0 constant, in that case, heat transfer to the system is solely used to increase the temperature, and its coefficient is now the heat capacity of the system with a constant volume. If there is no change in temperature, that is that can be achieved by attaching a system to a heat reservoir, keeping the thermal equilibrium in temperature T, so temperature doesn't change. In that case, the internal energy and temperature doesn't change. So this one disappears, and the only thing we have is the work done by the gas. That means because there is no change in the internal energy, nothing is left. That means accept the energy accepted by the system has been transferred to the environment by work. Heat is completely transferred to work. Okay. Next, the free expansion. In free expansion, we have looked at this free expansion already. Free expansion, change in volumes, the larger volume from a small volume against nothing. This is a vacuum. This vacuum does not carry any pressure. Because there is no pressure, 0 multiplied by cross-sectional area is the force. So vacuum does not apply any force against the gas. In reverse, by according to action and reaction, the expansion of gas does not require any work because of F equals 0, F dx integral F equals 0, so this is 0. The work PDV, P equals 0, this work done by the gas equals 0. We assume that there is no heat transfer, an adiabatic process. In that case, there is no heat supply. Heat supply, no. There is no work done by the gas. Work is 0. According to the first law of thermodynamics, delta Q is P delta V plus change in internal energy. And this is 0, this is 0, so delta internal energy equals 0. This one means the CV delta T equals 0. That means temperature is invariant. So free expansion does not change the temperature. Even though it expands, it does not work at all. That's the important point. Isobaric process that is a constant pressure. When the system is in constant pressure process, the work done by the gas, the integral dW is a delta W, and integral, this P is independent of V, so this integral becomes just a finite change. So P V final subtracted by V initial. That's it. This is the work done by the gas during an isobaric process. And according to the first law of thermodynamics, supplied heat is used to work. This is the work. Delta P equals 0. This is the work. And then remaining piece changes the temperature. So if I know the change in the temperature, I have to subtract the work done by the gas from the supplied heat to the gas system and divide it by the heat capacity. Next, we consider isothermal process. The first law of thermodynamics gives supplied heat is the work done by the gas plus change in the internal energy. And isothermal This means delta T equals 0. This is realized by attaching the system to a heat reservoir at temperature T. And it has enormous amount of heat. Either it can supply or get away of heat energy by keeping the temperature T the same all the way from the initial to the final state. So in the isothermal process, temperature is invariant. Temperature is invariant, therefore internal energy of the gas is invariant. This one leads to the identity supplied heat is completely used by the work done by the gas. And work done by the gas in isothermal process, that is a PV equals NKBT, isothermal temperature is the same. The pressure is NKBT, that is constant, divided by V. So work done by the gas during this process from Vi to Vf, NKBT is constant, and the log Vf over Vi. This is the work done by the system. So, because they are the same, the heat supplied to the gas should be the same as this. Okay? And next, constant volume process. If the process does not change the volume, then PDV, this one, must be zero. The work done by the gas is nothing. The first law of thermodynamics supplied heat energy delta Q is equivalent to the sum of P delta V plus the delta E internal. And the constant volume process delta V equals 0. Therefore, the supplied heat is completely transformed into the internal energy. And internal energy is CV times delta T. So temperature changes by delta Q over CV. All right. Adiabatic process, in an adiabatic process, it does not transfer any heat. So Q equals 0. If Q equals 0, this sum is 0. So work done by the gas plus internal energy change is 0. Then means internal energy change is the negative of the work done by the gas. If the gas does work, by that amount, internal energy decreases. If the volume of the gas shrinks, then the work done by the gas is negative, and therefore internal energy increases. Next, we consider cyclical process. Cyclical process, it makes a single cycle and returns to the same point. If the system is during this process, everything is in thermal equilibrium, every state is well defined, and well defined means we know everything: pressure, volume, and temperature. Everything is known. So when it returns, temperature is the same and volume is the same. Temperature same, so change in temperature after a single turn of a cycle, there is no change in temperature. That means no internal energy change. That means the heat transfer is completely transferred to the work done by the gas. There is nothing left additional or loss. There's no loss. So it's just temperature is invariant. So the gas system just to transfer the heat into work. It converts the heat to work. That's all. And then heat transfer mechanism. You know the radiator. Radiator we usually use a fin that has a wider area in a small space, just like a fin of fish. This is the reason why we use these fins in a radiator is to increase the rate of exchange of heat. Basically, heat transfer per unit time is proportional to the temperature difference between the high temperature and low temperature, the cold and hot, and it is anti-proportional to reciprocal to the distance of the two reservoir. This is hot and cold reservoir. And the rate is also proportional to the area. That's the reason why we use a fin to increase the area to let the radiation and faster. All right. And then we have additional factor that depends on the material. Sometimes insulator has a very tiny number, and these two expressions are identical to each other. This L over K is used as R, just like resistance. This formula is very similar to the for calculating resistance of a resistor that we study in the next semester. And the relation can be used twice for the series connection of two conducting material. You can follow this. So it is very similar to the calculation of a composite resistance, the equivalence resistance of a composite system, either series or parallel. In fact, the heat transfer, there are various one. The convection is a real flow of gas, and radiation is independent of medium that can transmit energy through electromagnetic radiation, just like the sunlight travel from the sun, and it travel along the long path that is vacuum and arrives at on the earth. So radiation power is proportional to the temperature to the fourth power. This is called the Stefan Boltzmann law. And before this, we have a spectrum of various wavelengths of radiation. And investigation shows that classical theory based on Maxwell's theory breaks down. It diverges. So people were wondering about the reason why, but Planck has found by accident, or he was so clever, without any mathematical derivation, complicated mathematical derivation, and he just fit it to the data, and he found a kind of condition. So that is called the Planck radiation. And finally, Einstein solved it. Einstein became to know how to explain the Planck radiation law. And in the end, the integral over the whole wavelength at a constant temperature that is called the blackbody radiation pattern, and that is integrated to obtain the Stefan Boltzmann law. And during the time, the Boltzmann's idea of statistical physics was applied, and Einstein's idea of a harmonic oscillator, the quantum harmonic oscillator, was used to explain everything. And later, uh, two classes later, we will learn what the Boltzmann factor is. And the Boltzmann factor is also used to completely explain the black body radiation that is on the on the verge of on the birth of in the time when quantum mechanics began. Okay, previously in the lecture we have seen the PDV. But PDV is we derive this using constant cross-sectional area of a piston that is a lid of a cylindrical container of a gas. And if it translates by dx, that changes the volume by dv. A dx is dv, and multiplied by the pressure, constant pressure inside the container to obtain the work done by the gas. But in fact, it can be done with arbitrary shape. And in the middle of a class, we introduced a way to describe the work done by a gas contained in a spherical container. And this is an explicit calculation for that one, and you can easily follow. You know how to evaluate the solid angle integral in the three-dimensional Euclidean space, and radial integral too. In the following classes, we need to know what Gaussian integral is. It is closely related to the Maxwell's distribution, Maxwell-Boltzmann distribution for the molecules in a thermal equilibrium at temperature T. It does have a function e to the minus x squared, and which we call Gaussian. And it is closely related to the normal distribution in the probability theory. And later, we will consider the central limit theorem that states uh, the binomial distribution approaches a normal distribution in the limit n goes to infinity. And the normal distribution is actually a Gaussian distribution with a normalization adjustment. So basically, this exponential minus x squared style function. So it is very important to know the normalization of such kind of distribution so that it is good to know how to evaluate this integral. This is a square root of pi. Let me explain how to do that. There are many ways to evaluate this integral, but a simple way at our level is just to square this integral. First of all, exponential function, whatever argument, it is positive definite. This is always greater than 0. And therefore, this integral is a positive definite. So I want to square it. And if I obtain the final result, what I have to do is just a positive of a square root. So that will be square root of pi. Let me square this integral, but this integral should be, two integrals should be evaluated independently. So I used different parameters. However, I can multiply these two as a double integral in the two-dimensional Euclidean space. That's fine. And let me introduce polar coordinates. Well, x equals r cosine, y equals r sine. Everybody knows. And we write this Cartesian coordinate double integral in terms of polar coordinate integral. We know how to do that, right? This is 2 pi, and it runs from radius, runs from 0 to infinity. There is no minus infinity because the radius is the square root of x squared plus y squared. It is always, there is no negative value for the radius. We substitute this relation. So actually, r is a Jacobian. And finally, this one, rdr. And this integral, theta integral is 2 pi, and we have rdr. And Leibniz told me it is just 1/2 r squared, right? This is 1/2 r squared. In addition, what should I do? Minus er squared d. Let me compute this. That is minus 2r d e dr e to the minus r squared. All right. So I have my negative sign on it, and this is just d. Oh, this is this minus 2r. This one is differential of minus r squared. So that means I have to erase 2, and the integral becomes a 0 to infinity, the total differential. And total differential disappears as r goes to infinity, that vanishes. If I substitute 0, that is 1. So this integral is a pi. As I told you, I is a positive definite. Therefore, I is the square root of pi. We can make use of a similar method. This trivial integral, this is a 1. We can rescale this integral by applying this alpha, but I don't know the answer. But this integral is a trivial too. It is 1 over alpha. By the way, we can take the derivative, partial derivative with respect to alpha. Then I have increased the power of x in front of exponential function. In calculus, you will learn how to compute this one repeatedly by applying integration by parts. But integration by parts, you have to repeat n times. And perhaps you need to evaluate a few times and use the mathematical induction, and it takes a very, very long time. But I have a way, simple way to partial derivative. The answer is this. And this is a way of defining factorial function in terms of integral. Due to this integral definition introduced by Euler, I can generalize this factorial function as a continuous function that is defined for all complex numbers except for 0, -1, -2, and so on. Except for these points, this function is absolutely integrable. And using this way, we can evaluate this integral and just to do it yourself. Is square root of pi, you know this. You can transform this one. If we substitute 1/2, this integral is exactly the same as the Gaussian integral. So the answer is the square root of pi. So that's the reason why gamma 1/2. That is equivalent to -1 factorial. This is defined. That is square root of pi. But usually we do not use half integers any except for positive, except for non-negative integers. You usually do not use factorial notation. So It's better to use a gamma function. Another interesting thing is you can multiply the Gaussian integral n times. That is trivial to find that. And similar change of variable to the polar coordinates is possible, but nobody knows. And there are many ways to evaluate the solid angle in n-dimensional Euclidean space, and there are a few papers written by our K-pop collaboration for teaching students how to compute that one, and you can find it in our homepage as well as in advanced textbooks, but then it will be very difficult for you to find everything. But anyway, in the end, the trivial result, this integral is known very well. And this is also trivial. So that is given in here. Because of this, you know how to evaluate n-dimensional solid angle. If you know the n-dimensional, this is a three-dimensional solid angle, and this two-dimensional solid angle, and the surface of the sphere is 4 pi r squared, and the circumference of a circle in two dimension is 2 pi r, and the volume of the sphere is this omega 3 over 3 r to the cube, and volume of the two-dimensional sphere, that is a circle, this omega 2 over 2 r squared, something like that. So we can make use of this formula to find out the volume or surface area of a sphere of radius r in n-dimensional Euclidean space. And in actual space, there is no Euclidean space with the four or higher we have never seen, but it does, they do exist in reality, in actual calculation. We have a chance to experience n-dimensional Euclidean space, although we cannot walk through by our foot. Okay, that's it for today. Thank you.